Hi all. Today we discuss theorems on the basis for a vector spaces. In order to discuss the theorems, we need to recall some results on the solutions of the linear system of equations. So for that we consider a system of linear equations a11 x1 plus etc plus a1n xn equal to b1. This is the first equation, etc etc. The mth equation is am1 x1 plus etc amn xn equal to bm. So this can be represented using matrices as ax equal to b, where a is the matrix aij. This is an M-bind matrix, and x is the column matrix x1 etc xn. These are called the unknowns. This is of order n by 1, and b is the matrix that is also a column matrix b1 etc bm, but order of this matrix is m by 1. So this system of linear equation can be represented using these matrices a, x, and b. Using this a and b, you can define the augmented matrix AB, and you can define the rank of augmented matrix and rank of A. These are two important quantities in the study of the solutions of this linear equations, system of linear equations. Or the rank of a matrix is defined as rank of a matrix A of order n by n is defined as the order of the largest subsquare matrix, square matrix or square submatrix, both are same. Subsquare matrix. The submatrices are obtained by deleting the rows or columns or both from the original matrix. Subsquare matrix whose determinant is non-zero. This is the definition of the rank. Whose determinant is non-zero. So using this definition, you can easily verify the rank of AB and rank of A. If these two quantities are same, if and only if we can say that the system is consistent. X equal to B is consistent. Consistent means it has at least one solution. Now using the if this is the case, that means rank of AB is equal to rank of A. Say we can write that as represented by R. Then if this n is depending on this R and n, you can say that it has only a finite number of solutions or infinitely many solutions. Okay, if n is equal to R, there exists unique solution. That is unique solution for unique solution. In the case when n is R is less than n, okay, R is less than n, R cannot be greater than n, because when you consider the matrix A, then the maximum possible order of a subsquare matrix is the minimum of m comma n. So that that order should be always less than or equal to m and n. So that means the rank is always less than or equal to n. So if n is equal to R, then there is a unique solution. Otherwise, that R, the rank should be always less than n if this is not the case. So R greater than n cannot be possible. Rank cannot be greater than n. So this implies there is infinitely many solutions. Infinitely many solutions. So this is the case. When b equal to 0, that system is called, when b equal to 0, we call the system ax equal to 0 is called a homogeneous system. Homogeneous system. In this case, the system is always consistent, because when you put x equal to 0, that means x1 equal to 0, x2 equal to 0, etc., then you can get at least one solution for this system. Okay, so homogeneous system is nothing but the system has at least one solution. System has has at least one solution. At least you can specify that solution. System has zero solution. You can use this as a characterization of the homogeneous system. If a system has zero solution, then if and only if it is a homogeneous system. Now the system Ax equal to 0 is always a consistent system. Okay, so Ax equal to 0 is always consistent. That means rank of A, B and rank of A should be same, because B is 0, then the rank of A, B is nothing but rank of A. Now here we have two possibilities, 1 and 2. The one possibility is the rank is the same thing, the rank is same as n and rank is less than n. If this is the case, then rank of A is equal to n, that is the number of unknowns, then we can say that the system has unique solution. That means only zero solution. Otherwise it has infinitely many solutions. Okay, that means there exists, otherwise there is non-zero solution. There exist non-zero values for x1, x2, etc., xn, which satisfies this condition, non-zero solution. So this is the classification of the solutions of a system of linear equation. We will use the last concept in case of the homogeneous system to discuss the theorems on basis. So, therefore, we can one more thing. One more time we can discuss the last one, the classification of the solutions of homogeneous system. The homogeneous system is always consistent. Then there are two possibilities. It has only zero solution, that is unique solution, and infinite many solution. So the unique solution is obtained from the condition rank of A equal to the number of unknowns. If the number of unknowns, the rank is always, if the rank is less than number of unknowns, then you can say that it has at least one non-zero solution. Okay, of course it has. If it has at least one non-zero solution, it may have infinitely many solutions. So this is the classifications of the solutions of homogeneous system. If rank of A is equal to number of unknowns, then unique solution, that is zero solution, only zero solution. Otherwise it has infinitely many solution. Then of course it has at least one non-zero solution. Now we can discuss theorem 1. If S is the set of vectors v1, v2, vn is a basis for a vector space V, then any set containing more than n vectors is linearly independent. That means if you are given a basis first, it contains n vectors, then any number of vectors more than n vectors, that is always linearly dependent. Okay, so we will prove this theorem by taking a set of vectors containing more than n vectors, then we will prove that that is dependent. For that we assume a subset T consisting of vectors u1 etc. up. Okay, our assumption is P is strictly greater than n. So this is a subset of V. We will prove that this set is always linearly dependent. To prove this, we need to consider the linear combination of the vectors u1, u2, etc. up. That is c1 times u1 plus etc. Cp times up equal to 0. We will prove that all these coefficients are not 0. Okay, if all these coefficients are 0, we can say that this u1, u2, etc. up are linearly independent. We need to prove that this is linearly dependent. Okay, so we will find, we can easily find a non-zero set of non-zero values for the c1 and c1, c2, etc. cp. That means not all ci's are 0, which satisfies this condition. Okay, so first you assume this one. Now this u1 is a member of V, and v1, v2, vn is a basis. Then u1 can be expressed as a linear combination of v1, v2, etc. Okay, that means any vector of V can be expressed as a linear combination of elements of S, because S is a basis, therefore S is a spanning set. So you can easily find out the coefficients a11, a12, etc. an1 such that a11 times v1 plus etc. an1 times vn is equal to u1. Similarly, you can find out coefficients corresponding to u2 and named it as a21 v1 plus etc. a2 a this is a1n, this is an2. We'll write this is a11 and this is the second here the second term is a21 v2 plus etc. And here we have a12 v1 etc. a n2 vn, and the last one is up corresponding to up. We write a1p v1 plus etc. anp vn. So we can easily find out all these coefficients. Now substitute these values in this equation. We replace this u1 by this expression, so we can get c1 times a11 v1 plus etc. an1 vn plus c2 times u2 is a12 v1 plus etc. an2 vn plus etc. The last one is Cp times what is Up? Up is A1p V1 plus etc. Anp. This is A1p V1 plus etc. Anp Vn equal to 0. Now you rearrange this by collecting the coefficients of V1 first. Then this can be written as a11 times c1 a11 times c1. This is the coefficient of the v1 in the first term, and from the second term you can get a12 times c2 plus etc. From the last you can get a1p times cp. These are the coefficients of v1. Then you write this times v1 plus, now collect all v2. Then the first coefficient should be a21 times c1. So that's from here. The second coefficient here, the expression of u1, we have a21 times v2. Okay, so c1 times c1, then we have c1 here, c1 times a21, that is a21 c1 plus etc. Finally we can get a2n c n is a2p, right? a2p cp times v2 plus etc. The last one is a n1 c1 plus etc. anp cp times vn is equal to 0. But we know that v is a basis, s is a basis, as considered of v1 v2 vn. So this v1 v2 vn are all linearly independent vectors. So this is a linear combination of v1 v2 etc. vn, but v1 v2 vn are linearly independent. Then all these coefficients should be 0. Now you can, this expression implies that due to the linearly independence of this v1 v2 vn, you can get a11 c1 plus etc. a1p cp equal to 0 and a21 c1 plus etc. a2p cp equal to 0. All the coefficients are 0 etc. an1 the last one is an1 c1 plus etc. anp cp equal to 0. Now we have a system of linear equations in this p unknowns, say c1 c2 etc. cn. Now you can write it as a times instead of x I write c equal to 0. This a is an the entries of a from a11 to anp. So this is a n by p matrix. A is an n by p matrix, and C is a p by 1 matrix. The C consisting of the vectors C1 etc. Cp, and this A is nothing but Aij and a zero vector. Okay, so this is a homogeneous system of linear equations. We have seen that this has a solution if and only if the rank of A is equal to the number of unknowns. So this is always consistent, but we know that the maximum the rank of this A is always less than or equal to n and p, but we know that this p is always greater than n. This p is greater than n. That means the rank is always, the rank is here, the rank is always less than or equal to these two quantities. Rank of A is always less than or equal to these two quantities. So we can say that the rank is strictly less than this P. Okay, here P is less than n and the rank is always less than or equal to these two quantities. So we can say that rank is less than P for this matrix. Then this coefficient matrix has the rank which is less than the number of unknowns, say C1, C2, etc. Cp. So therefore, the system has infinitely many solutions. Okay, it has unique solution only if the rank is same as the number of unknowns. From this, you can write the system. Okay, the system has A C equal to 0 has at least one non-zero solution. Non-zero solution. That means there exists a set of scalars C1 etc. Cn, Cp, which are not all zero and satisfies this condition. If it satisfies this condition, then it satisfies this condition as well, because this system is obtained from this equation. That means there exists a non-zero, not all zero scalar C1, C2, etc. Cp such that this is equal to 0. Therefore, the vectors u1 etc. Up is linearly dependent. That means any set of vectors, more than this n is always linearly linearly dependent. Okay, that means the maximum possible number of linearly independent vectors in a vector space is nothing but the cardinality of the basis of that vector space. That is the theorem 1. The next classes we will discuss the other theorems on this basis of a vector space.